All right, now we're going to mop up with just a few final thoughts about aqueous solubility. We're going to talk about the effect of pH, we're going to talk about cosolvents, and we might even talk a little bit about surface films and natural organic matter. So we're going to have later in the semester a whole lecture on the acid-base chemistry of organic chemicals. Some organic chemicals do have the ability to either take up a proton and become positively charged, that would make them a base, or some have the ability to lose a proton, causing them to be negatively charged, and those are what we call acids, right? Not all chemicals can do this, but some can. And so in the case of chemicals that do have this acid-base chemistry, then the pH is going to have a big effect on the solubility of the compound. And of course, I really emphasize the fact that pH has an effect on the apparent solubility of the compound. The intrinsic solubility of the neutral form of the chemical is not affected. But the charged form, whether it's a positively charged base, a conjugate base, or it's a positively charged acid, negatively charged acid, either way, if it has a charge, that species is going to be much more soluble in water, because water loves to solvate things that have charges on them. So if you added together the solubility of the neutral form with the solubility of the ionized form, then together, those two summed together would be much higher than the solubility of just the neutral form by itself. But notice the intrinsic solubility of the neutral form is not changed, right? It's not affected. It's just that you have to add on top of that the solubility of the anion or the cation. And we'll talk about this a lot more when we look at acid-base reactions, but it's important just to measure it, just to mention it here. Then we're also going to talk about the effect of dissolved organic matter. Again, this can increase the apparent solubility of a compound because dissolved organic matter is by definition dissolved. So if you try to filter it out of solution, you can't do it. It runs right through the filter. And the chemicals can actually zorb onto that dissolved organic matter. So they are sorbed to the dissolved organic matter, they go right through the filter, and what you capture on the other side, the filtrate, might have very high concentrations of your chemical. They might even be in excess of what you think the solubility is, but that's only because there's this extra pool of your chemical that is sticking to the dissolved organic matter. And we're going to talk about this a lot more when we get to the lecture on sorption. We'll have some math behind it, and we'll explain how it works and talk about how you might predict it. But for now, I just want you to know that this is a possibility, and that again, the intrinsic solubility of the compound is not affected. It's just that there's this extra pool of the compound that might be sorbed to the natural organic matter. Then the last topic I want to touch on is the effect of cosolvents on solubility. Remember, I was saying a good example of a cosolvent system is beer, right? Beer's got 6% ethanol in water, and that changes the properties of beer. So presence of a cosolvent can increase the solubility of hydrophobic chemicals because the ethanol is less polar than the water. So the mixture of ethanol and water is slightly less polar than water just by itself. And if you're talking about a nonpolar chemical, it'll be a little bit happier dissolving in a liquid that is a mixture of ethanol and water and therefore slightly less polar than water. So its solubility will be enhanced. And this becomes important in several instances for environmental people. One is where you have industrial wastewaters. They can have very high concentrations of all kinds of nasty chemicals, and they can even have concentrations high enough where they start to act as cosolvents. Another important example is, what we used to call, when I was a kid, we used to call it gasohol, but I don't think we use that term anymore. I think people usually use the term E85, which is, I think it's 85% ethanol in gasoline. But systems where you have a mixture of alcohol and gasoline, those can be, we use them frequently to combat climate change because the ethanol sources are frequently biomass sources. And if you have a leaking underground storage tank that's full of this gasoline alcohol blend, it gets out into the groundwater. The ethanol dissolves in the water, and then you have this ethanol water mix in the groundwater that is now changing the solubility of many chemicals, making them much more soluble. So now they're going to be more movable, they're more mobile in the subsurface because this alcohol water mix can be moving downstream and carrying higher concentrations of toxic chemicals like PAHs with it. This is also an important concept when we have engineered systems. So frequently, if you have soil or groundwater contamination, they will use soil washing or aquifer washing approaches where they inject a solution of water with a cosolvent in it into the groundwater. that increases the solubility of all those chemicals that are sitting in the aquifer and allows you to strip them out and remove them. So you inject in one well and then you go down gradient and extract that stuff in the down gradient well, and it comes up having stripped away a bunch of these chemicals that you're trying to get rid of. And then another example where this is important is when you're doing high-performance liquid chromatography. In virtually every form of HPLC that you do, your mobile phase is going to be a mixture of water and a cosolvent. And it's the proportions of water and cosolvent frequently is what you adjust over the course of a chromatographic run in order to change the retention time. And so what you're doing is you're changing the amount of the chemical that you're analyzing that can be dissolved in the mobile phase versus how much of it is going to be sticking to the stationary phase. So it's an important concept and worth spending, a moment or two to talk about. So when we have this discussion, we're going to focus on chemicals that are not very soluble to begin with, because those are the ones that are going to have the most effect from the cosolvent. Things that are very soluble to begin with, what do we care if their solubility changes a little bit? It's the stuff that's just not very soluble to begin with that solubility can change a lot if you add just a little bit of cosolvent. And we're going to also focus on cosolvents that are completely water miscible, right? So these would include things like methanol, ethanol, propanol, right? Acetone, dioxane, acetonitrile, dimethyl sulfoxide. These are two things that you might have encountered if you're doing HPLC. They're frequently used as cosolvents in HPLC. DMF, dimethylformamide, also very commonly used in HPLC. Glycerol, frequently used in those kinds of groundwater remediation systems that I was talking about, because glycerol is pretty biodegradable, so you can feel safe injecting it into an aquifer. And what all these solvents have in common is that they're relatively polar and they can hydrogen bond. And for that reason, they're infinitely miscible with water. So in general, the solubility of a chemical increases exponentially as the cosolvent fraction increases. And you need about 5 to 10% by volume of your cosolvent to start to see an effect, which is why I like to use beer as an example, because it's just there at the threshold where there's enough ethanol to really make a difference. The extent of the solubility enhancement depends on the type of cosolvent and the solute itself. So the effect is greater for the things that are really big and nonpolar and have low solubilities to begin with. And it's also greater for cosolvents that have more organic nature to them. So methanol has only got one carbon with a hydroxyl group on it, right? But ethanol's got 2, and propanol's got 3, right? So in general, propanol is the most nonpolar or the least polar of these 3 solvents. So it has a greater effect on solubility than ethanol, which has a greater effect than methanol. So here's a bunch of big, complicated diagrams from the book trying to explain this concept to you. So we'll go through these. So the first one here, this is the log of the activity coefficient. Remember, René Schwarzenbach loves his activity coefficients, versus the volume fraction of methanol, from essentially 0 methanol, pure water, over here to 100% methanol, pure methanol. And then each of these lines is a different chemical. Down here you've got aniline. Okay, so aniline starts out with a relatively low activity coefficient, meaning a relatively high solubility, and that activity coefficient increases by maybe an order of magnitude here as you increase from 0 to 65% methanol in your system. So you've enhanced the solubility by an order of magnitude. And then as you go up here, you've got trimethylaniline. So it's got 3 methyl groups. It's still an aniline. It can hydrogen bond, but it's a little bit bigger and more hydrophobic. It's experiencing a solubility enhancement of about, I would say, about 1.5 orders of magnitude over the same span. Naphthalene, totally nonpolar. It's experiencing a solubility enhancement of, I don't know, what would you say, about, maybe 1.5 orders of magnitude. But then you get to the PCBs, large hydrophobic chemicals. Here we're going from about 6.2 to about 2.5. So you're talking about almost 4 orders of magnitude solubility enhancement. And 2,4,6-trichlorobiphenyl now has 3 chlorines, very big molecule, going from about 7.5 down here to about 3. So 4.5 orders of magnitude solubility enhancement by changing the volume fraction of cosolvent. So the take-home message there is that the bigger and more hydrophobic the chemical, the larger the effect of the cosolvent. which is again why we tend to focus on the most nonpolar chemicals. The ones with the lowest solubility to begin with are the ones that experience the most enhancement. Okay, the next plot is showing 3 different cosolvents, but the same solute. Same solute, 2,4,6-trichlorobiphenyl, so we know that that's the one up here that had the most solubility enhancement, so big hydrophobic chemical. And then how its solubility changes as, again, solubility really expressed in terms of activity coefficient, changes as you increase the volume fraction of cosolvent. For methanol, the enhancement here is not as huge because methanol only has 1 carbon. So among the 3 here, methanol, ethanol, propanol, methanol is the most polar and therefore has the smallest change on the properties of the water. Ethanol, a little bit bigger solubility enhancement, and propanol has the biggest solubility enhancement of all. So here you're holding the cosolvent types steady and changing the solute. Here you're changing the cosolvent but holding the solute steady. And then down here, this is the solubility enhancement. So how much the solubility is enhanced, the log of the solubility in pure water divided by the solubility or the activity coefficient in the cosolvent mixture. So that's the solubility enhancement. And now it's plotted as a function of the molar volume of the solute. Okay, and so we've got some numbers here for PCBs and some numbers here for PAHs and also some numbers here for anilines. And the difference between the 3 groups on the bottom here and the 3 lines at the top is that the top ones are 0.4 or 40% cosolvent, and the bottom ones are only 20% cosolvent. Okay, so PCBs, biggest, most hydrophobic molecules, having the biggest enhancement in solubility, and as the molar volume of the solute changes, the enhancement and the solubility gets really, really big, right? So the enhancement is a little bit less for the small PCBs and most for the really big PCBs up here. Same thing for PAHs, solubility enhancement somewhat for the small molecular weight PAHs, but a big solubility enhancement for the large PAHs. Anilines are relatively polar and have high solubility to begin with, so their solubility enhancement is not huge. The slopes of these lines are a little flatter, but it's still true that the bigger the aniline molecule, the larger the solubility enhancement. Okay, so it is possible for us to develop these types of linear relationships between the cosolvent fractions and also between the molar volume of the solute to describe the solubility enhancement that you might see when you add cosolvents to your system. And that's what's shown here. Those are these equations that we could come up with. So the solubility of your compound in a certain concentration of cosolvent, a certain volume fraction of cosolvent, is equal to the solubility of that compound at a different volume fraction of the same cosolvent, plus this sort of correction factor here, which has a term sigma, which is a slope term and depends on both the solute, cosolvent, and the solute. And then here, this is the difference between those 2 volume fractions of cosolvent. Now, it's not that common that we're really looking at the difference between 10% ethanol and 20% ethanol. Usually what we're looking at is the difference between no ethanol at all and some ethanol. So that's what this equation is doing. It's saying let's express the solubility enhancement or the new solubility of our chemical at this volume fraction of cosolvent as a function of the solubility of the compound with no cosolvent at all and just plain water, because that's a number that we can look up much more easily. And now, same equation, you got sigma, which is a slope term that depends on both the cosolvent and the solute. And then instead of multiplying it by the difference in the volume fractions, we know that in this case, the initial volume fraction was 0. So now we just have to divide or multiply by the total amount of cosolvent. So it could be 6% or 10% here. And the slope here, the sigma, is something that we would determine from these kinds of plots that we were just looking at. So I think it's worth, talking a little bit about this and explaining to you how cosolvents work, because as I said, there's a lot of examples where it becomes important, but we're not going to go into too much detail here. I think that's about all I wanted to say about cosolvents, but I do want to touch on one other subject, which is surfactants. So surfactants are interesting chemicals right? And you may have heard of surfactants. I hope that they talk to you about surfactants in your organic chemistry class. Surfactants are characterized by having a part of the molecule that is water-loving or hydrophilic, meaning polar and probably hydrogen bonding, and then a long tail over here, which is nonpolar, and therefore it is hydrophobic, which is another way of saying lipophilic. It likes to dissolve in lipids. Okay, and because of this, sort of unique structure, what happens when you put a bunch of surfactants together into some water, at first they hang out separately. They're all kind of swimming around by themselves. But at some point, when you reach what's called the critical micelle concentration, the CMC, these individual chemicals get together into something called a micelle. And that's where all the hydrophobic tails are pointing toward the center, creating a little hydrophobic zone in here. And all the heads are pointing out toward the water because they're polar and want to hang out with the water. And the interesting thing about the micelle is that it's creating a whole new little world inside the water that can do interesting things. So if I'm a giant molecule, like benzene, right? I'm hanging out in the water. I'm very nonpolar. I'm not happy here in the water. I might find this very appealing, and I might find a way to worm myself into the center of that micelle so that I don't have to be dissolved in water anymore. Instead, I can find my little hydrophobic bubble and be happy there. And this is exactly why surfactants are used to clean things. That's what soap and detergent is surfactants. Because if you have a greasy stain on your shirt, grease is not very soluble in water, but if you hit it with some soap, with some surfactant, the grease will find its way into the center of the micelle and then get washed away when you wash the surfactant away. So this is tricky because, again, the surfactants are generally not going to be present as monomers. Once you hit the critical micelle concentration, the CMC, they're going to be present as micelles. And so there is no such thing as CW set for a surfactant. And where this becomes important to us as environmental people is some of the emerging contaminants, like the perfluoro compounds, are surfactants. Perfluorooctanoic acid, PFOA, is a surfactant. And so if you want to go look up the solubility of PFOA in water, you ain't going to find it. Or if you do find it, it's not going to be very meaningful because it forms micelles. Really what you want to do is look up its critical micelle concentration. And then these micelles can have very, very high concentrations. You've seen, when you use your dish soap, you can have dish soap that is, very, very concentrated dish soap, has very little water in it, or you can mix some water in it and make it less concentrated. That's why they say, a drop of Dawn will clean a whole load of dishes. That's because that drop of Dawn is very, very concentrated surfactant. But essentially the surfactants, because they form micelles, are pretty much infinitely miscible with the water. So it's very difficult to describe their solubility. So we can look at it from both points of view. From the point of view of the surfactant itself, which could be a perfluoro compound, it affects their environmental fate. And then from the point of view of other organic chemicals that are not surfactants, the presence of other surfactants changes their fate. Makes them more soluble, because if they're here in the center of the micelle, they're now quote-unquote soluble, right? They're not going to be filtered out. Even though they're not technically dissolved in water, you can't filter them out. So it might affect their fate in the environment. And the really interesting thing about surfactants, too, is that a lot of organic molecules that arise from natural organic matter are also surfactants. They have maybe carboxylic acid groups with long chains on them, so they behave like surfactants. And if you put them in a water tank or in the surface of a lake or a river, the hydrophobic part of the surfactant will like to stick out here in the air because air is the equivalent of a hydrophobic solvent, right? It has no polarity at all. So the non-polar part of the surfactant will stick out toward the air, and the polar part will point down toward the water. So a lot of these surfactant-type molecules will hang out right at the surface of the water column, and they will change the properties of the water column. They'll change the properties of this tiny little layer at the surface, which we call the surface microlayer, SML. And so by having all these surfactant molecules here, you've made a slightly more hydrophobic region here right at the tip, right at the surface of the water, and hydrophobic contaminants might really like to partition there. So that can change their fate. And it can have a big effect on the air-water exchange, because for a hydrophobic chemical to get from water into air, it's got to pass that layer. And if there's a layer of surfactant there with maybe a bunch of hydrophobic chemicals in it, that might slow down their mass transfer. So the investigation of the surface microlayer is a really active area of research for a lot of people. They do a lot of sampling and trying to understand it. And I don't think we really at this point have a good handle on exactly how it affects the fate and transport of organic chemicals, but we know that it definitely does.